Good morning, good evening, and good afternoon, everyone. So welcome to this Hadoop tutorial for beginners from Simplilearn, where you would learn about Hadoop, you would learn about its processing framework, that is YARN, you will learn about the programming model, which is MapReduce, and much more. So in this Hadoop tutorial, we will learn about what and why of Hadoop. We will learn about Hadoop's distributed file system, that is HDFS. We will learn about Hadoop MapReduce, which is a programming model, or I could say oldest and most mature programming model. You have Hadoop YARN, which is taking care of resource management and use cases of Hadoop. Finally, we would see some demo on HDFS, that is working with the distributed file system, working with MapReduce and also YARN. So the question is, why Hadoop? Now let's understand that with an analogy. Just imagine in a town far away, Tim sells food grains in his shop. The customers were happy as Tim was very quick with the orders. And Tim sensed a good demand for other products, so he thought of expanding his business. But it wasn't easy as he expected it to be. The number of customers were increasing and he was not able to cater to their needs on time. He had to look into assisting his customers with each of their orders and billing. It was too difficult for him to manage alone. So what does he do? To start delivering orders on time and to manage the customer's demand, Tim hired 3 more people to work with him. So it was Tim, it was Matt, Luke, and Anne. Now there was still a problem. The problem was with storage area. So solutions which Tim was looking for was that he should have enough space in the shop for all the items so that he can cater to different customers for their different needs. And as it seems, storage was a bottleneck, since storing and accessing became more and more difficult with increased supply and demand. So what does Tim do? So Tim came up with an idea to overcome this issue. He basically decided to expand the storage area and distribute each category of product on different floors. Now that's a smart thinking. Customers were happy, and after picking up their products from the respective sections, the products could be built. Now if we compare this simple story of Tim to what we call as big data, let's talk in technical terms now. So we know that data has been critical and important for organizations. However, in past, data was generated at a moderate rate and all the data was structured in nature. So when I say structured, data can have different types. Data can be structured, it can be semi-structured, and it can be unstructured. Now when we talk about structure, semi-structure, or unstructured, the main difference is presence or absence of schema. So if you can have schema defined well before the data comes in, and then your data fits into that schema, we would call it as structured. If you have intelligently defined your schema, expecting your data to get stored within that schema, however, the data pattern breaks it, then we are talking about unstructured data or absence of schema in the data. You could have semi-structured data, which basically means that you could have a mix of structured and unstructured data. Now, in past, data was mainly structured and pretty much one processor was enough to process all of it. Now, as the data generation increased, there were different types of data which were getting generated, or I would say different type of data sets which were getting generated, and that too with a high speed. So it was evidently becoming difficult for a single processor or a single machine to store, to cure, to process, to mine, to analyze different types of data and data sets. Now with different types of data existing and they getting generated in massive amount, it posed a challenge that this data could not be processed and stored, and the known storage solutions were traditional databases. To overcome this issue, multiple processors were used. So this is where we started seeing a shift in paradigm from single processor to multiple processors, or I would say from a vertical scalable solution to a horizontal scalable solution. So when you say vertical scalability, we talk about increasing the capacity of a machine. When we talk about scalability, we mean a capability to scale, capability to expand. And when we talk about a single processor, that is vertical scalability. scalability, where you would have one machine or one server with limited amount of RAM, limited amount of storage, and you could think of expanding that by adding more RAM, adding more storage. But that would have some limits. You could not go beyond a particular limit. You probably would have to be locked in based on the vendor, because you cannot change your internal components to suit your requirements. And if we talk about horizontal scalability, that is multiple processors in this case, we are talking about adding more machines so that you could have a horizontal scalable architecture. Now, the problem which we were talking about, to overcome that issue, multiple processors were used to process each type of data. And here we see a similarity in Tim's approach with the technical approach of going for a distributed platform which could handle huge amount of data coming in different formats, data getting generated with a lot of speed, and thus helping the organization. Now what happens is, when you think of having multiple solutions or having multiple systems which can be used to store or process your data, one of the major challenge is one storage system being accessed by all the machines becomes a bottleneck. And that is again a problem, similar to what Tim was having when he decided to cater to multiple customers looking for different products, but then he was limited with the storage space he had and to keep all the products in one place. So just like how Tim adopted the distributed approach, the storage system, which was a bottleneck, was also then distributed. So in this way, your data could be stored in individual databases or in individual machines on their disks. However, it could be accessed from one place. So if we look at this story, we see two approaches. And these two approaches are the ones which are used by Hadoop, which is a framework. And these approaches are your storage layer, that is your HDFS, and your processing paradigm, that is MapReduce. Now, what is HDFS? Let's understand this. HDFS stands for Hadoop Distributed File System. So that's a logical storage layer. It's a distributed storage space, just like our example of Tim having distributed the storage space amongst various sections. So each person was taking care of a separate section, and at the end, the customers went to the cashier for the final billing. This sorted the process and made it easier. Now this is how similar, or this is how Hadoop MapReduce works. Now that was a rough story of big data generation and why Hadoop is required, right? Let me explain what Hadoop is. So if we talk about what is Hadoop, it's basically a framework. It's not a programming language. It's not an architecture. It's not just a hardware. It's not just a software. It is a framework which allows you to store and process big data in a distributed and parallel fashion. Now there are a lot of users which have made big data case study a famous and a popular one. So here are some companies, say Facebook or Instagram, Google, Twitter, LinkedIn, Skype, YouTube, and many more. And these and many more organizations across the globe are using Hadoop for their storage and processing requirements. However, it would not be just Hadoop. Hadoop also comes with its own ecosystem, which has various set of open source technologies and packages, all packaged together to help an organization in various facets of its data life. So the question is, how does Hadoop store and process all of this data? Or I would say this big data. Or before we even talk about Hadoop, which has individual components which are responsible for storing and processing big data, we also need to understand what is big data. So big data is just a term. Data has been exponentially growing in past decade, and now we don't talk about gigabytes or terabytes. We already are talking about petabytes and exabytes, or even zettabytes, that is 10 to the power 21 bytes. However, in known factors, any organization is not processing zettabytes of data, but yes, there are organizations which are processing petabytes and exabytes of data. So how does Hadoop help them, and what is this big data? So big data is a term coined to explain the data which is very complex, which is huge, which is getting generated with a lot of speed, which has a lot of variety, and then it becomes a challenge to store, to capture, to analyze, process this data, and derive useful information out of it. Now we are talking about huge amount of data. we are talking about different V's, that is V for volume, V for velocity, V for variety, V for veracity, and other aspects like viscosity, validity, virality, and many more. So when your data comes in with all these characteristics, it can be easily categorized as big data. And organizations in recent past have realized that they cannot ignore any data considering it as uneconomical. So they would want to work on all of it. And when I say all of it, that is one of the drawbacks in terms of RDBMS. So in RDBMS, usually you will never have 100% of data online. You would still have your data. It would be consistent. You could do transactions, but you would not have access to all 100% of it because that would be a costlier option. So in RDBMS, you would have 10 or 20 or 30% of data which would be online, and rest of the data would be archived, which basically means that if you would want to process that data, you would have to bring it from the storage layer to the processing layer, process it, and then store it back. Now, how does Hadoop help in this approach or this requirement? So when we talk about components of Hadoop, we have a storage layer, that is HDFS. Now, you can compare this with your own laptop or PC. Every laptop or a PC has two layers. It has a storage layer, that is your disk or your external hard disk, which is attached to your machine, and your machine also has the processing layer, which is your RAM and CPU cores. So HDFS is the storage layer of Hadoop. So it's a logical storage layer, which technically speaking does not exist, but then yes, it exists because it depends on the individual file system of multiple machines. We'll learn about this in a few minutes. The other layer is the processing layer. So when you talk about MapReduce, it is a programming model which allows you to process the data in one particular way. Now, MapReduce has been oldest and the most mature. So when I say most mature, it has evolved over time. Since the time Hadoop came into existence, MapReduce exists. It is still being used by organizations for doing processing. And when we talk about processing here, we are not talking about processing on one single machine, but we are talking about processing on multiple number of machines where each machine's RAM and CPU cores contribute to the processing. So we have two main components. One is your HDFS, one is your MapReduce. And for your MapReduce or basically any other processing framework, MapReduce is one of them. So for any other kind of processing, say massive parallel processing, say graph processing, say MapReduce processing, say structured query language being processing, for all of these processing needs, there is a processing layer called YARN. Now YARN stands for yet another resource negotiator. So basically YARN takes care of your resource management. That is, when the processing happens across the machines, who would take care of RAM and CPU core which would be required for processing, and that would be your YARN. Let's learn a little bit more on the storage layer, a distributed file system which belongs to Hadoop. So Hadoop Distributed File System is known for its distributed storage method. Well, it derives its functionality, or would be say is inspired based on Google file system, wherein you would have your data stored across multiple machines. So HDFS also distributes the data among many computers or many machines. Let's take a simple example here. Take an example of you working on your profile or your resume and you would like to go to your friend's place. Now you have two options. One, content in a pen drive. Take the pen drive with you, go to your friend's place, plug in the pen drive, and voila, there you have your file. The second approach is you can have your file uploaded to a Dropbox or basically attached to your mail and save it as a draft, and you could be at your friend's place opening up your mail and reworking on your document or your resume or your profile. Now in this example which I just mentioned, for you, your Yahoo Mail or your Dropbox or some other web site where you are uploading your document is like a logical storage layer. Well, you are uploading your document, but that document is not getting stored within your mailbox. It is basically getting stored on the underlying servers which are being used by Yahoo or Dropbox or basically any other social media website. So for you, you have a storage layer which allows you or gives you the feel that your data just exists for you to access it. However, that data is residing on one of the underlying machines or servers which the service provider has. So similarly, when you talk about HDFS, it is a logical storage layer which distributes the data among multiple machines. So for user, it is a storage layer where you can write your data. You could be writing your data to HDFS, you could basically create a copy of it, and you could do many other things with your data, and your data gets stored on HDFS, but technically speaking, it gets stored on the disks of lot of underlying machines. And in addition to this, whatever data gets stored on the underlying machines is auto-replicated to some other machines so that you never have loss of data. Now here we see that we are talking about block of data which is stored. So if you would have a file which you would want to store in a Hadoop cluster, now when I say cluster here, I mean multiple machines plugged in together to serve a functionality. So if you would be writing in a file, depending on the size of file, the file would be split into blocks. We'll learn more about that. So as of now, you can understand that the file would be split in blocks, and the blocks will be distributed across your underlying machines, and each block which gets stored on one underlying machine is also having its replica or multiple replicas across different machines. So if we talk about a 500 MB of data which is getting stored in a traditional method, we would say this is how your 500 MB data would get stored. So you would have entire data that is getting stored in one database or underlying file system, right, which may overload the database, which may overload the file system, and the fault tolerance is pretty much zero. So if your database crashes, if your storage layer crashes, if your file system is not accessible, then you lose all of your data. So this is more of a data sharing architecture where you say that the data is getting stored in underlying database or underlying file system, and then it is being shared or accessed by multiple applications or multiple users. If we talk about Hadoop's storage layer, that is HDFS, the problem is taken care because the data is distributed across multiple machines. So if we look at this image, it explains that the same 500 MB of data which was getting stored in one location in a standard solution would now be getting stored across machines, so that one single machine is not overloaded, and second, you have your data distributed across multiple machines. And as I mentioned earlier, your data is split in blocks, and each block is replicated again on different machines. So that gives you an idea that even if one or a couple of machines fail, you would not have a complete loss of data, or in fact I would say you would have no loss of data because your data has replicas existing on some other machines. So HDFS is actually designed for storing massive data sets in commodity hardware. Now when we say commodity hardware or commodity machines, we mean something which is not as big or as powerful as a carrier class hardware, but it's not even as small or less powerful as your simple desktop or laptop. So commodity machines is basically machines which have good amount or mediocre amount of RAM and CPU cores, and then you could have multiple of these used to set up your cluster, and that would be serving your distributed file system. Now HDFS again has two main components, or I would say this logical layer is functional with two different processes or two different components which would be running on different machines. So you have a name node and you have a data node. So as we see, name node, as it says, it is something to do with name, and data node is something to do with data. So name node is the master of the system, or I would say master of your cluster, master of your storage layer, that is HDFS, and it basically stores all the metadata. So that already explains that name node is really critical because it stores the metadata. It is the master, which basically also means that if your name node crashes or the machine where name node process is running, if that machine crashes, then you would have no access to your cluster. So there are a lot of ways in which that could be made highly available. There are concepts of high availability. There is a concept of federation, which basically allows having more number of master machines to make your cluster more stable, and also to store your metadata in multiple locations. Data node is the slave machine or the slave node, or I would say slave process, which is running on one or multiple machines. Now here we are talking about horizontal scalability. So name node being the master would be running on one machine or multiple machines depending on the setup, such as high availability or federation. However, data node, which is the slave node, would be running on multiple machines. The more number of machines you have, the better. More number of machines you have, it would give you more scalability, more processing capacity, and more storage capacity. So data nodes are the ones which are taking care of your read-write operations, and they are the ones which are storing the actual data. So which basically means if I have a cluster of 10 machines and my one machine is master, which is name node, then I can have data nodes running on all the 10 machines if I would want my data to be stored across all the 10 machines. However, the best planning strategy would be that you would have name node running on one single machine, and you would not have data nodes competing with name node for resources and storage. So in a cluster of 10 machines, I could have one name node and 9 data nodes. That means the disk of these 9 data nodes are contributing their storage for HDFS. Or I could say in another way that whenever you write data to HDFS, your data would be actually getting stored in the underlying data nodes, or 9 of these data nodes. Let's go further. Now, if you see here, it also explains your interaction between your slave and master. Now, name node is a master, so it's not name node's responsibility to ping every machine and check if it is available. In fact, it is other way. Your data nodes are sending signals or heartbeat every 3 seconds to the name node. So as soon as your cluster comes up, as soon as you start your cluster, you would have name node running on one of the machines and data nodes running on multiple machines. And as soon as the cluster comes up, data nodes will start sending packets of information to name node, so that name node can register the information of which data nodes are available in the cluster. Now, this initially is only from data nodes to sending heartbeat to name node, registering their information, confirming their availability. So the actual data is getting stored in data nodes, and data is in the form of again a logical entity called blocks. So the default size of each block is 128 MB, and that started with Hadoop version 2. So prior to Hadoop version 2, we had the default block size 64 MB. However, there is no limit. You can, on the other side, you can have, whether it is Hadoop version 1 or Hadoop version 2, your block size could start with the default size, and then they could even go to gigabytes, terabytes, petabytes level. However, in organizations, you would always observe that the default block size is 128 MB. So if we talk about this 530 MB file, it's very obvious that it cannot get stored in one block. Now this file would be split into multiple blocks. So let's imagine your file 530 MB is being written to HDFS, and it would get split into 4 blocks. Each block can contain up to 128 MB data. So my block A would have 128, block B would have again 128, block C would have 128 again, and block D would have 128. So we are talking about 256 plus 256. That basically makes it around 512, which would not be enough for your 530 MB file. That's why we would need one more block of 128 MB, which could hold the rest 18 MB data. So that's how your file would be split and stored in multiple blocks. And remember, each block which would get stored on a data node would have a replica of itself on 2 other data nodes. So the default replication is 3 and the default block size is 128 MB. Both of these parameters can be customized. So you can set your block size to something else. You could set your replication to something else. However, the default is replication as 3 and block as 128. So to store a file of 530 MB, you would need at least 5 blocks. And if I say replication is 3, then I would technically have 15 blocks getting stored across machines. Now, if we see this part, the last block, it says 18 MB. So remember one thing, your block is just a logical entity. So for a file of 1 kilobyte or 127.99 megabytes, it would still use a block of 128 MB, which does not mean there is a space wastage. Block is just a logical entity to take your data to the disk. So when you write, imagine you write a file of 1 kilobyte on HDFS, it would call in for a block of 128 MB. The block then gets stored on the underlying disk, and when it gets stored on the underlying disk, it will only use 1 kilobyte of disk space. And if we consider replication, then you can say 3 kilobyte of disk space across machines. Now that's how your HDFS works. Your data could be stored, either all the blocks could be stored on data node 1, and then they could have their replicas on data node 2 and data node 3, or randomly, when your blocks are distributed, you could have all the blocks spread across multiple machines, and then their replicas would be existing on other machines. So the first rule of replication, just to mention here, is that any particular block would not exist with its replica on the same node. Or I could put it in a different way. I could say you will never ever have two blocks which are identical getting stored on the same data node. Now all these blocks are getting stored in data nodes. Now what happens if the block or the node containing block A crashes? So do we lose the data because the underlying machine has gone? And that's the beauty of HDFS, that we have something called as auto replication. And that is mainly to give you more fault tolerance. That is mainly to prevent the loss of data. So if one particular machine goes away, we already know that this block A would have replica existing on two other machines, and you can have your data access from one of these machines in the cluster. So the user doesn't have to worry if a particular machine has crashed or gone away, provided the data was replicated and it was stored across multiple machines. Now, I could also say that if you had enabled replication as 1 and you did not have copies of your blocks, and if the data node containing the block crashed, then potentially you have a chance of losing your data or not being accessible because you did not enable replication, or you did not set the replication to more than 1. Now, your HDFS is smart enough, or I would say name node is smart enough to handle your data node failures. So what HDFS offers is auto replication feature. Any data which is being written to HDFS, depending on its size, would be existing in one or multiple blocks, and each of those blocks are automatically replicated across your machines on the cluster. And if a particular data node, or if I have a replication of 3, and within this, if I lose 2 machines holding my block and its replica, then I still have the third machine where one more replica exists, which potentially gives me a chance to get back my data. I don't need to worry about any kind of data loss. So this is how it would look. So if you have block A, which is getting stored on data node 1, and we also have the concept of rack here, which we can talk later. So you would have the same block A having its replica on 2 other machines, and that could be, those 2 machines could be belonging to a different rack. So you have the replication achieved here because block A exists with 2 other copies. Now, one point to remember here is, in Hadoop or in HDFS, you don't have any difference between original block and a replica of it. It basically means the same. All of them have the same power or status. Now, if you talk in terms of rack awareness, that is, if you have a cluster where machines are placed in racks. Now, what are racks used for? So in organizations, racks are a systematic and a logical way of keeping your machines together. So you could have different kind of setups. You could have one rack holding all the machines which have only master processes running, or you could have other option of each rack having a machine with a master process and rest machines would be slave processes. Now, whichever aspect we talk about, if your machines are placed in rack, then the second rule of replication kicks in. Now, what was my first rule of replication? You will never have 2 identical blocks sitting on the same machine. So block A and a copy of block A cannot be existing on data node 1 or 2 or 3 or any of this. Now when we talk about machines being placed in rack, and if your name node is made aware of it, if your cluster is made aware of it based on configuration, then the second rule of replication kicks in, which basically means you will never have a block and its replicas all residing on the same rack, even if they satisfy the first rule. So even if you would say, well, my block D is having its replicas on some other machines, and I would want to have all these machines in one rack. Well, you could do that, but that does not give you a redundant solution. There can be other solution also, as we see here, where your block 2 is spread across 3 different racks, and that's okay, but that's not preferable because then you're increasing your bandwidth requirement. So the rule of rack awareness, or how the blocks are placed, if your cluster is rack aware, is that you will have something like what we see for block B or block A, where you would have block B on data node 4 and its replicas on some other rack on 2 different machines. So even if one rack is lost, you still don't lose your data because there are copies of that block existing on some other machines on some other rack. So this is how replication in HDFS offers fault tolerance, and it basically gives you the flexibility of working with the cluster without being bothered of which of the underlying machine is not performing well or is not available. So that's about your name node and data nodes and your blocks being placed. Remember, your block size can be customized, your replication can be customized, and that basically would apply at a cluster level. Let's now spend some time in understanding the architecture of HDFS, that is basically your Hadoop Distributed File System, how it works, and how do these different components contribute to the functionality of HDFS. Now what we have learned is that name node is the master of your cluster, and it's also master of your storage layer, right? So name node basically takes care of storing metadata of the cluster in its RAM and also in its disk. How does that happen? So when a particular cluster starts, you would have your data nodes coming up and also your name node coming up. And as we discussed earlier, your data nodes will start sending heartbeat to name node every 3 seconds as soon as they have come up. So data nodes are sending their heartbeat to name node, and name node has started registering this information in its RAM. So this is the first kind of metadata which name node has in its RAM. Now name node also has some metadata in disk which would have been created when before starting your cluster you would have done some formatting. So usually when you would want to set up a cluster, you would basically have the Hadoop related packages downloaded on all the machines, which would have Hadoop related directory. It would have a config directory where you would have your config files, and based on that you would have decided that some of your machines would run data nodes and then which machine would be having name node running. So in the beginning, when the cluster is about to be started, the first thing which is done is a formatting, and that formatting actually creates metadata in the name node's disk. Now this metadata contains your file system image, that is what does your Hadoop cluster or file system contain before even it is started. It has basically the identifiers of the cluster such as namespace ID, cluster ID, and block pool ID, and all this information name node has in its disk. So name node cannot come up if this metadata in disk does not exist. So once the metadata in disk exists, you can go ahead and start the cluster, and that's where your data nodes will send heartbeat within 3 seconds of coming up to the name node, so that name node starts registering this information in its RAM. So that's the first metadata which name node has in its RAM. So as I mentioned earlier, your racks are basically available in organization because they would want to store their machines in a systematic way, and your racks could have machines where your master process would be running or your slave processes such as your data nodes would be running. So if you have racks available, then the replication would make sure that the blocks would be placed in such a way that you would never have a block and all its replicas on the same rack. So with the machines placed in racks, the the rack placement policy makes sure that all the replicas, as I mentioned, will not be existing on the same rack. Now that is when you have racks. So if a client has a read request, it will always first contact the name node, checking that it is interested in reading a particular file and where can it find this file. Now name node basically checks the metadata in RAM because it initially has information of your data nodes which are available. But not only that, if there was data written earlier to the data nodes would also be sending every 10 seconds the block report to the name node. So as soon as the data nodes come up, they send their heartbeat, making name node aware about their availability. And when the data was written to HDFS, data nodes would be also sending their block report every 10 seconds to the name node. And this is additional metadata which name node is storing in its RAM. So basically name node has information of what are the data nodes available, what are the files which are written to the cluster, the files are split in which blocks, the blocks are sitting on which data nodes, and what are the file permissions. So whenever a client would want to read some data, it would contact name node. Name node would look into its metadata and then it will respond back with a ordered set of data nodes where the replicas or the blocks can be found. Now once the client gets this information, your client can read the data from the underlying data nodes. Now that's how a read is happening, and this would happen in a parallel fashion from multiple data nodes. When it comes to write, it is a similar process that if a client would want to write some data, it would contact name node. Name node would give a list of data nodes which are available where the data can be written, and then basically client would write the data directly to these data nodes. So in this fashion, your HDFS basically handles the read and write where name node is an important component. Now these are some of the features of your HDFS. So as I mentioned earlier, HDFS offers fault tolerance because of the multiple copies of data which are existing across data nodes, and that is due to the auto replication feature which HDFS has. When it comes to data security, your HDFS provides end-to-end encryption that protects the data. Scalability wise, since we have multiple underlying nodes which can be used for your read and write, and also you can add any number of nodes to the cluster, which basically makes scalability one of the features of HDFS. When it comes to flexibility, Hadoop is flexible in storing any type of data. As I mentioned, it can store structured, semi-structured, and unstructured data, and data which is getting generated in huge volume and with a lot of velocity. So these are some of the features of HDFS which makes it an appropriate solution for storing huge amount of data with an intention that you would want to read, write huge amount of data, and also process that data for your different business requirements. Now that we have stored our data in HDFS, what's the purpose? Any organization would want to store huge amount of data with an intention that they would want to process it. And for processing, Hadoop has its programming model, that is MapReduce. Now, MapReduce is one of the oldest and most mature processing programming model, which is little rigid. It is batch oriented operation, but then it allows you to process huge amount of data which is spread across your cluster. So if we compare traditional approach, big data was processed at the master node, or it is still master node is one which is playing an important role. So your slave machines or your data nodes are the machines where your data is actually getting stored. Now, like your HDFS as the storage layer, you also have a processing layer called YARN. So in case of HDFS being the storage layer, you have name node as the master and data nodes as the slaves. In the same way, for your processing layer, resource manager is the master and node managers are your slaves. And node managers would be co-located with data nodes. So if you would want to process huge amount of data from multiple machines, how would you do that? And that's where MapReduce comes in handy. So if data has to be processed, there has to be some mechanism where instead of moving your data from the storage layer to processing layer, you would want to process the data wherever it is stored. Now that is an approach which MapReduce uses. Hadoop has this data locality reference, which basically means do not move the data from one layer to other layer, but process the data wherever it is actually stored. So let's understand what is MapReduce and how it works. So as I mentioned, it's a programming technique. It's a programming model. However, it does not depend on one specific programming language. So you can have your MapReduce programs written in Java or Python or Scala, any programming language. So it's a programming technique, it's a programming model where huge amount of data is processed in parallel and in a distributed fashion. So when you talk about MapReduce, as the word itself says, it has basically two phases. One is your mapping and one is your reducing. So mapping phase is taken care by a mapper function provided by the developer. Reducing phase is taken care by a reducer function, which is again provided by the developer. And these mapper and reducer functions internally run map and reduce tasks. So if you would want to understand this better, let's look at this. So for example, you have your data stored on HDFS. Now we know that depending on the size of data, it would be split and stored in the form of blocks across your machines. Now for your map and reduce, the first thing is the input data has to be divided in the form of input splits. So by default, your each split is equal to the block size. Or I could tell this in a simpler term that if your file has two blocks, it would mean that your MapReduce or your map task has to work on two splits, each block being one split or one chunk of data on which the processing would start. So as I said, your mapping phase is basically something which has your mapper function, and mapper function would have the code for map task which would run on one or multiple split. So each split has to be processed, and then there is an intermittent result which is your output from mapping phase. Now this data might be coming in from one map task or multiple map tasks. So basically there would be some kind of shuffling and sorting wherein the output of mapping phase is then grouped together so that it could be further processed. Then we have our reducing phase, which depends on the reducer function, and this reducer function does the reduce task of working on one or multiple inputs coming from the output of map phase. So reducing does the aggregation and finally creates a final output. So here if you look at this, your mapper function is provided by the developer, which takes care of your mapping tasks. Your reducer function is again provided by the developer, which takes care of reducing tasks. Your sorting, shuffling, also we have partitioning, which decides how many reduced tasks would be used. All that is taken care by the framework itself. Now looking further, let's see how MapReduce works with an example. So this is my input data, which is basically one line, or you can say three lines, which has to be processed. So we have input data which says welcome to Hadoop. Hadoop is interesting, Hadoop is easy. Now this could be split. Imagine that this data is huge, probably more than 128 MB. So imagine this file would be then split into multiple blocks, each block acting as a split, some portion of data being in every block. So these are your input splits. So imagine this file is split, and then you have welcome to Hadoop as one split, Hadoop is interesting as other split, and Hadoop is easy. So these are the input splits which will have to be worked upon by your mapper function. So your mapping phase, where your mapper function would work on each split, would consider every line as a record. Now remember, Hadoop has different formats. So the default format is text format. However, Hadoop supports your input format in different ways. So the main task of your mapper function or the map tasks is to work on every record or work on every split and convert that into list of data elements which are nothing but key value pairs. So if we take an example of a traditional word count where we would want to count the words in a file, your mapper function would basically look at every record. It will break each record into list of elements, that is words here, and with every word we have one, the value given to every word. So here we have the word as the key and the value is 1. Now this is the output from your mapping phase. But if I want to do a word count, this is obviously not my final output. So what happens next? So once your mapping phase complete, this data then has to be shuffled and sorted so that the similar keys can be brought in together. Now that would obviously help the further phases. Now once the sorting and shuffling is done, you would have this data being handled by reducing phase. Now, before it goes to reducing, you might hear something about partitioning phase, which basically decides on the keys how many reduce tasks might be required to work on this. So here we see our type of keys are words. So we could easily assume that there would be one reduce task which would work on this shuffled and sorted data. And your reducing phase can then aggregate all the keys which are similar and count the values or increment the values. So your final output would be again a list of elements which are nothing but words and their total count which we wanted to do. So when you talk about your MapReduce, it has good load balancing. So you have map and reduce tasks. Now remember, your map tasks have to complete before the reduce tasks could start. Now the data being split is done by framework. The splits are being worked upon by map tasks, and your reduce tasks would then work on the output of map tasks. Now there is also something called as re-execution of tasks. So for example, if a task map or reduce fails on one of the machine, your MapReduce programming model doesn't give up. So you would have a re-execution of the tasks on either the same node or on a different node, and all that re-execution and everything is taken care by the processing layer YARN. So it's a simple programming model, but yes, we have to agree it is little rigid because whatever processing you do using MapReduce has to follow mapping and reducing paradigm. It's one of the simplest programming language which is based on Java, but as I mentioned, it can also be coded in any other programming language. So if we talk about HDFS, it's a storage layer. MapReduce, it's a programming model, and both of them were and are important units in Hadoop. So with Hadoop version 1, there was a limitation. So the MapReduce version 1 was a kind of limitation. Now the limitation was in the way the processing was handled. So in case of Hadoop version 1, the processing layer had a master called job tracker, and then you had your slaves called task trackers. But the problem was that job tracker was not only responsible for doing resource management or resource allocation, but it was also taking care of job execution. Now that was a problem because in this case, job tracker was overburdened because it was listening to all the task trackers, it was tracking their resources, and it was taking care of processing. So if a task failed, then it was the work of job tracker to basically restart or re-execute that task on some other machine. Now that sounds like a drawback. So job tracker being overburdened was kind of a bottleneck. Now in Hadoop version 2, YARN was introduced. So YARN, being a processing layer, can support different kind of processing frameworks. So in Hadoop version 1, the only kind of processing we could do is MapReduce, and no other processing was possible. But from Hadoop version 2 onwards, with YARN being introduced, we can and we could do different kind of processing on top of your Hadoop clusters. So what is YARN? As I mentioned in the beginning, YARN stands for yet another resource negotiator. Now that is something which brought more powers to your Hadoop clusters. So when we talk about YARN, it is a resource management layer or the processing layer of Hadoop. Now we discuss HDFS is for storage, MapReduce is one of the ways to process the data, but who takes care of the resource allocation? Takes care of negotiating the resources across your cluster on multiple machines. And that is what YARN specializes in doing. So YARN, the processing layer, has a master which is called resource manager. Now this is replacement to the master in Hadoop version 1, which was called job tracker. So your resource manager at a higher level, you could say, manages the assignment of resources such as CPU, memory, and your disk. Node manager are your slave processes. Now this is a replacement of task tracker in Hadoop version 1. And remember, node managers would be co-located with data nodes. So if we have 10 data nodes, you can easily understand that there will be 10 node managers running on the same machine wherever data nodes are running. The new or the another negotiator which we talk about is application master. So it's a simple piece of code which runs whenever an application is submitted and whenever resource manager has already negotiated resources with node manager. So how does this work? Now let's imagine a client would want to do some processing. Now here we should remember that the client would have already interacted with name node, getting an information of which machines are available, where the data exists, and where the processing could be done. Name node would have internally responded back with the information that the data which client is interested in lies on XYZ data nodes. Then your client contacts the resource manager. Now resource manager, which is the master, is keeping a track of the resources which node managers have. So every node manager is like a worker process which has some allocated amount of resources. So for example, we can say that if every machine had 10 CPU cores and 20 GB RAM, then say some percentage of those resources would be allocated to node manager on every machine to take care of your processing. Node managers are not only sending heartbeat, but they are also communicating their resources to resource manager. Resource manager is the one which is listening to the client and is also tracking the resources which node managers have. Now whenever a particular client wants to do some processing, your resource manager will make a request to node managers for resources. So for example, if your application needs 6 GB of RAM and 4 CPU cores, your resource manager could be requesting these resources to node manager. So for example, here in this case, your resource manager will negotiate the node manager 1 for 3 GB RAM and 2 CPU cores, and similarly 3 GB RAM and 2 CPU cores to the second node manager. So this request of holding resources which will be used for processing is called container. So instead of we calling every time resource manager asking for RAM and CPU cores, we could easily say resource manager requests a container of some size. Container definitions are already defined in the YARN configuration file. So once resource manager requests these containers, node manager, depending on the load what they have, depending on the resources they have, will communicate back to resource manager about their approval on these containers. Now once the container is granted, or once the node manager has promised that it can give the container to resource manager will start an application master. So here we should remember application master is a temporary daemon which will run only till the application executes, which also means for every application which is submitted to the cluster, you would have one application master. So what does this application master do? Application master would basically use this container and it will get the execution of application done. So the question is, where does this application master run? So from the requested containers, your application master would also run in one of the containers that is in some amount of RAM and CPU core, and it will use the other containers for getting the execution done on the machines wherever the relevant data resides. So this is what happens. So your client program sends an application request to resource manager. Resource manager is already getting an information of which nodes are available, what is their capacity, how much resources they have, and so on. Resource manager would then, based on the job request or application request, contact the node manager requesting for containers. Node manager grants the request, and then your resource manager would start application master, basically saying take care of the execution, and once the execution of application is done, come back and communicate to me. Application master, which is a piece of code, will run in one of the containers and will use all the other containers to execute the tasks. Now here we should remember one thing. Resource manager, being the master, is the only one which can negotiate or ask for containers to node managers. At any point of time, if an application master needs more container, for example, a node manager or a machine crashes, an application master cannot use the container on that particular node. In that case, application master will always contact the main master, that is resource manager, to negotiate more resources. Your application master cannot directly request resources to node manager. Now that is what happens in YARN. So YARN has an internal component called scheduler, which takes care of job scheduling. So YARN is responsible to process your job request and allocate resources which are required. With this capability of YARN having an application master, which is a temporary daemon, YARN supports multi-tenancy, which basically means different kind of processing can now happen on YARN, which also means we can have multiple users which would be using the cluster, and you could even have different versions of MapReduce or other processing framework possible on YARN. Now, when we talk about scalability, when we talk about our cluster, we would already know that there can be huge number of nodes, and those nodes can be dynamically added to the cluster, which basically gives us a possibility of a scalable processing layer. Now, so that basically tells us one thing, that Hadoop is a solution which companies would want to use if they would want to process big data, if they would want to store big data. And many companies are already using Hadoop. So when we talk about Hadoop, there are many other solutions in the market which would compete or mention that they could do it better than Hadoop, or they could do what Hadoop is doing. And that's not false. However, the success stories of Hadoop are quite a lot, because Hadoop has been in the market for quite some time and it is being used by various companies. So when we talk about companies, there are different companies. You can always look at huge list of companies by just typing in Google companies using Hadoop. One such use case is about Pinterest. So you might have heard of the popular image sharing website called Pinterest. Now this is how it would look. So you have different categories here, and it basically offers you different kind of images. So Pinterest is a social media platform which allows you to pin any interesting information you find on its website. Think of the traffic, think of people who would be visiting this website, think of the user related data or usage related data that would be getting generated. So Pinterest has more than 250 million users and nearly 30 billion pins. All these account to big data concerning Pinterest. And as I said, it's not just about providing a functionality. You would have a lot of users logging in, you would have user related data, probably their behavior related data, probably how website responds to different users, and these different pins on about which customers find something interesting. So the problem here was Pinterest faced a challenge in processing tremendous amount of data. And as I mentioned, this is not just a case of Pinterest. There are a lot of companies which are working with big data or are interested in working with big data. And the biggest challenge is storing this data and processing this data when the data volume is huge. So if you would want to store or continue capturing or curing or mining or analyzing this big data, and if you would want the data which needs to be displayed in users' personalized discovery engine, that would certainly be a problem. What was the solution? Hadoop. Hadoop, with its features like HDFS, which allows you scalable storage, auto replication, fault tolerance, and flexibility to scale with a processing layer such as YARN, makes it available for an organization like Pinterest, which could not only store huge amount of data but also could easily process this data. So Pinterest uses Hadoop to process and analyze big data in a way that it helps the company to show the most relevant content to its users. And that's a win situation for a company which started using Hadoop. Now, through continuous analysis of the data, Pinterest can provide its users with features such as related pins, guided search, and so on. Now, this is how Pinterest benefited from Hadoop. So, one of the recommendations here is, if your organization or if you would want to work on so-called big data, if your interests are in storing, curing, capturing, mining, processing, and analyzing huge volume of data which contains a lot of variety, which gets generated with a lot of speed, which has other characteristics like viscosity, validity, virality, volatility, you should be using big data. So I would suggest, let's start using Hadoop and put an end to the big data challenges which we might be facing in absence of a solution such as Hadoop. Let's also look at a quick demo on using HDFS, MapReduce, and YARN, which will clear our concepts on HDFS, MapReduce, and YARN. Now that we have set up a 2-node cluster, which has 2 data nodes, 2 node managers, 1 master machine, let's try working with HDFS. Let's look at quick commands which allow you to write data to the cluster, although there are different ways. The first way is using commands. The second is using an IDE, and where you could write your code to use Hadoop's file system API. And the third is a graphical user interface called Hue, which normally does not come with Apache. Although it can work with Apache, it comes as a service with Cloudera and other distributions. To work with HDFS, we need some sample data. Now there are various websites from where you can get some sample data. So you can open up your browser and let me show you some sample places or sample data set links from where you can download bigger or smaller files, which then can be used to write data to your HDFS. Although you could just pick up a local file, or you could create your own files and write them to HDFS. There are various dataset sites which can be used. So for example, you can type in machine learning UCI datasets, and this is one link which has more than 200 datasets, which can be used for even data science kind of activities, which can be used for testing with your algorithms. And you can download data from here onto your local machine, and then from your local machine we will be writing the data to HDFS, which then, based on the size of the data, splits the data into blocks, and your blocks would get stored on your underlying machines wherever data nodes run. So I can click on this UCI machine learning repository, or even just on data sets to be very specific. All we need is some sample data sets. You can get Kaggle data sets, you can get data sets from Yelp website, which are bigger data sets, zipped, and you can be using them to write data to see how your file split into multiple blocks. Now here we have a lot of data. We can click on any one link to begin with, and here I have the data folder, shows me some file, and I can just right click on this, save link as, and save the file. This is a simple text file, and we can save it. And you can get various data sets from here. You can even go to Yelp dataset challenge, and that has bigger files which are zipped and they can be downloaded. So you can click on download dataset. Although I will not start the downloading here, you can just give in your name here, just some email ID, some initials, and you can click on download. So this is one more website where you can download the JSON datasets, which are 3.6 gigabytes in compressed format, and then you have photos which are in 7.2 gigabytes. You can also say Gutenberg download books, and that is again a website from where you can download free datasets which are not very huge. So try to get some variety of datasets in different formats, which then you can write to HDFS. You can even use your HDFS log files which already exist on your machines, and you don't need to download anything from internet. Now let's close this for now. So I already have some file. Let's copy this from home, HTC downloads. That was my file. Let's copy it to home HTC, and here's my file. I can check the permissions. So that's owned by HTC. I can even look into user local Hadoop logs, and there are some already log files. So you can even copy some of these files using copy user local Hadoop logs, and let's take Hadoop data node related log, and let's copy it to home HTC for our testing. And now we have some other files. Now to work with HDFS, as I said, you can always type in HDFS, and that shows you various options. Now we already used the first option, which is name node -format. We also used HDFS admin to look at how many nodes we have, and to work with your HDFS file system, the option is DFS. So you would say HDFS, DFS, and then you can always hit on enter, which shows you various options to work with your distributed file system, like creating a directory, copying some files, getting data from your HDFS to your local machine, changing the permissions, changing the replication, and many other options. So here, let's click on HDFS, DFS. Let's create a directory and let's call it my data. So this is a directory I'm creating on HDFS. Remember, this directory will not be seen on your local machine. It is a HDFS directory. Now, if I look in my root, I don't see my data because that's a HDFS directory which is technically getting created on HDFS, and once you start writing data to HDFS, the relevant blocks will start getting stored under ABC/data. So as of now, we can always keep a browser open to see, as we work with HDFS, how does the data propagate or come to your distributed file system using the web interface. So here, let's say http://m15070, and that's my browser interface. Let's click on utilities and let's click on browse the file system, which should show the directory which we have created, although that does not have any data as of now. Let's go in here. And now we know that we have some files here. So I will say HDFS, DFS, and this has two options. Either I can say put or I can say copy from local. Both of these do the same thing, and both of these you can find here. So we have put and we should have copy from local. That is, you're copying the data from your local machine to your HDFS. So now I will say copy from local. I will say take the ABA directory or file and put it in my data. So now I'm technically copying a file from my local file system to my HDFS, which is then using again my local file system's path. So this is done. Let's quickly check by clicking on my data if my file is written. Now if you see, this file is 187 kilobytes. However, this will still use a block of 128, and in my previous sessions I already explained why a block of 128, but when it goes to the disk, it will only occupy the space for the data the block has. We can quickly go in here and we can do a HDFS DFS listing of my directory, which should have my file now, and we can quickly check if my file is replicated, either using the web interface which says replication is 2. That means the file related blocks should be getting stored on the underlying data nodes. We can always click on overview if we would want to browse and scroll down, which says there are 3 files and a directory. The file has 1 block, so totally you have 4 file system objects. We can scroll down to show or see we have 2 live nodes, and if you see, each node has 1 block. We can always look from our data path by looking into ABC/data/current, that has block pool directory, that has current, that has finalized, that has subdirectory, and the block. Look at the size of the block. It is 191, which relates to the kilobyte size which we are talking about. Similarly, we can check on M2 machine, which also has a data node running, to make sure our file related block is replicated. So look in block pool, current, finalized, subdirectory, and that shows me the same block which is replicated with its meta file and with the same size. This ensures that my data is getting replicated as per whatever factor we have set, and my file is written to HDFS. And now I can also do a complete listing. I can just say a recursive listing to show me all the directories and all the files which I have in my HDFS. I think we are forgetting something. We are logged in as root, which is not right. So we need to be logged in as HTC, and then we can try our commands, that is HDFS DFS-ls / which should show me my directory. But then if you would want to do a recursive listing of showing all the directories and files, you can just add -r. So we have written a file to HDFS in my data directory. Similarly, I can write using a put command. Last time we used a copy from local. I will use a put command. I will say let's take this log file and let us write it to the my data directory. Instead of copy from local, I'm using a put command, which also allows me to write the file to my HDFS. Once this is done, let's go to the web UI and let's go to browse the file system. Let's look in our directory, and that shows me that I have a log file which is even smaller than the first file which we wrote. It is in kilobytes. However, it is replicated. It is using still the block size, and we can always go back and look at the terminal to see if for my new file I have a new block which should be in my data path. And if you see this is my block, which will also have a replication on machine 2. So this is how you write one file, or you could write multiple files. Let's create some files here. So I have these log files. Let's say Hadoop log, and let's give it a name like this. So now if you see, I just created multiple files, and I can also say HDFS, DFS, make directory, let's say my data 2. So I'm creating a new directory on my HDFS, and then I can even copy multiple files or a complete directory. So all I need to do here is give a matching pattern or a directory. So I'll say HDFS, DFS, put, and then I can say take all the directories of files and put it to my data 2. Remember, this one file or multiple files are following the replication what has been set at a cluster level. Now if we do a recursive listing where I would want to see all the directories and the files which are within my HDFS, I see that I have a my data directory, and I also have a my data 2 directory which has multiple files, and all of the files within the directory are following the replication set at a cluster level. So all of them are having their blocks replicated twice. We can always go back here. We can just do a back, and that shows me what I have in my data 2. Everything is replicated twice. What I have in my data is also replicated twice. Now HDFS also has a functionality where you can write data with a different replication. So let's create one more directory, and now let's write data with a different replication. So the way I write my files, I follow the same thing. However, now I will say -dfs.replication, and I will specify it as 1. So I'm passing in as argument, and I'm specifying that I would want to write data with a replication of just 1. So my blocks will not be considered under replicated, and I'm choosing to write these files in this directory with a replication of 1. We can check from our browser interface by just doing a quick refresh. And here, if I click on my data 3, it shows it follows a replication of 1. There is also a command to check your replication status using HDFS. So we can say HDFS fsck/files/blocks, and if I would want to see only blocks or only files, I could choose one of them. Now here I have given a complete HDFS file system. I can replace that with /my-data. So I can say my data 3. This is what I would want to see, and this will show me within this directory how many files I have, how many blocks does each file use, and is it replicated correctly. So my fsck command gives me an information that in my data 3 I have one file which is 24 kilobytes, uses one block because it is very smaller than 128, and it is replicated only once. So there is no situation of over under misreplicated blocks. We have our files correctly replicated as they were specified while writing. Same thing can be seen for other files, say my data 2, and that will tell me that all the files within my data 2 were replicated as per the default replication, which was at a cluster level. And if you see here, everything is replicated twice. We don't have any over under misreplicated blocks, and my file system status is healthy. So this is the HDFS command to make sure that your files are replicated correctly. So we have seen how your files are written with default replication. We have seen how your files follow a dynamic replication, what you specify on the command line. Now we can also see a command which allows us to change replication after the data has been written. So I can say set rep, and I can say path, that is my data 3, where I initially had all my file related blocks replicated only once, and now I'll say my data 3, and I can specify that this should follow a replication of 2, which basically means that it will look into the directory, it will check all the files which had only one block, and now it will create a replica of those blocks across other data nodes. We can always go back and look into the data node logs to see the replication happening. We can also look from the browser interface, which initially was showing a replication of 1 and now it shows a replication of 2. So this is the command to change the replication after the data has been written. So our writes can have default replication. We can write files with a different replication. We can change the replication after the data is written. Not only that, we can even get the data from our HDFS to my local machine. And for that, I'll give HDFS get command or copy to local. So I can say my data 3, and then I can bring it to my local machine in home HDC using a get command. So this is to get data from your HDFS to your local machine using a HDFS command. Now if you see, I should have a my data 3 directory which is in my local path, and we can look in my data 3. It has all the files which we had on HDFS. So we were not only putting data from our local machine to HDFS, we also successfully brought data from our HDFS to local machine. We have written data with different replication. We have checked the status of nodes. We have checked the status of blocks, and if we would want to delete some data, HDFS also has options for that. So I can say HDFS DFS remove, and I could also do a recursive remove to remove everything including the directory from my data 3. So this will delete data from my HDFS. However, if thrash is enabled, now thrash basically means recycle bin, which depends on a property in the core-site file. We have not enabled it. If thrash is enabled, then your data will be deleted from HDFS. However, it will not be permanently deleted. It will sit in thrash for a time interval what admin has specified in the configuration file. So right now I deleted thrash, and this seems to be gone from HDFS because we have not set up any thrash. However, if a thrash is set up, then either you can decide to have your data deleted and still be in thrash so that it could be restored, or you could delete it permanently using a skip thrash option. However, remember, this skip thrash option makes more sense if the thrash is enabled in your cluster and you do not want your deleted data to be sitting in thrash even for whatever time interval has been set, because even if the data sits in thrash and your thrash is a directory structure on HDFS, all the data will still be replicated. So we have seen how you can write data to the cluster, how you can get data from cluster to your local machine, how you can write it with different replications, how you can delete it from your cluster, and do a recursive listing of your directories and files. Now there are various other commands which can be used. For example, something like copy or move or change permissions and many more. So the more you would want to try, type in HDFS DFS, and that shows you different options which can be used to practice working with HDFS using commands.
Now that we have looked at understanding MapReduce, understanding HDFS and YARN, let's have a quick demo on a simple MapReduce program which could give me a total count of URLs or websites which were most frequently visited. Now for that, I have a sample file here and I would be using those. So if you look into my file, this basically has a list of URLs and some counts already, although we have some URLs which are repeated. Now you could have a huge list of URLs from either a script or a basically different program which has given you an initial count of the URLs which were visited by users in different locations or in different sites. And what we would want to do is we would want to work on such file and get a total count of URLs based on users who have visited these URLs. So what I would want is to look into a huge file which has list of URLs and a count for each URL, but then I would want to have a cumulative count of user visits for a particular URL so that I can find out which URL was the most popular one and which URL was least visited. So let's take this as an example. Now for that, if I would want to use a MapReduce approach, I would need a mapper class which does the map task, and here we have our mapper class which imports basically some packages which will be used by my code. I have my mapper class called URL count that extends mapper, and it expects data in particular data types which are Hadoop specific, that is text, int writable, and so on. And here we would be interested in working on the file where we would try to get the key and value out of the file. Now our key would be the URLs and value would be the initial count which shows up in the file. Now what do I need? I also need a reducer which basically will do a aggregation. And what does this do? This will overall look at all your key value pairs, and based on the keys it will aggregate the values if the key is repeated. Now this is my map and reduce, but then I also need a driver program which basically would tell me what is my mapper class, what is my reducer class, what would be my output key format, and what would be my value format. And also in the configuration I am setting a property which will allow me to read key value pairs wherein they are separated by space as a delimiter. Now once you have your code written, that is your driver program, your mapper, and your reducer, you can basically export this into a jar file, and here I could just select the project, and then it shows that this is the location where I would want to save my jar file. I can just say finish. If it already exists, it will ask me to overwrite it, and I'm okay with that. Now once your jar file is ready, we also need to closely remember what is the package we are using and what's my class name. Now once you have your jar file, you also need the file existing on your HDFS so that you can do MapReduce. Now let me just log into a cluster here, and that's my login details. I will just paste the password and hit enter. So I'm on web console, and if I do a listing, I see that there is the jar file which I just created, and there is also a url.txt file. Now here we can look into this url.txt file, and that has some data here. Now we can add some more data if we would want to look at different URLs. Let's say if users have visited Yahoo, especially the mail part of it, and then I will say might be 20 times. Then you had Yahoo being visited from a different location, and that was 3 times. You have say people visiting google.com, and let's say Gmail here, and I would say 12 times. Let's say again google.com/gmail from a different location, and that was 4 times. Let's say http// and let's say url1.com, and that was visited again 8 times recently, and so on. So now this is my sample file, and what I would do is I will just put it on HDFS in this particular location. I'm using a -f option because the file already exists, and I'm just trying to put the updated one. Now once this is done, we are good to run our MapReduce, which will look into these list of key value pairs, which are nothing but URLs, and a count of users visiting these URLs. So for this I can say Hadoop jar, and then I need to mention my jar file which has my class, and my package name is this one, and then my class name was this one. Now I need to give an input, so I will say user, my directory, and within my directory I have a file called url.txt, and I would want my output also, so I will specify my directory, and then let's say url output, and let's call it 1. So this will be the directory which will be created, which will have the result of my MapReduce on this file, which should give me a cumulative count of how many times a particular URL or a website was visited. Now let's run this. So this is basically submitting your MapReduce job to a YARN cluster. We could also run MapReduce in a local mode. Now we see it is connecting to resource manager. It will first go through the mapping phase. Now here we have only one file to process, so it basically went for one map task, and then it would go for one reduce task. Now if we also look in, this will tell me what was the map input record, so each line is considered as a record, and when we say output records, it has broken down that into list of unique values. Now that becomes an input to your combiner phase if in your driver program you have mentioned a mini reduce, that is your combiner. If none, then the output of your map becomes the input of your reduce phase, and reduce finally gives me the list of URLs and their count. Now since my job has completed fine, I should be able to look at my output directory, which is this one, and whenever a MapReduce runs, depending on the number of reduce tasks, we would have one or more part files created as an output. So let's have a look at this. What does my output contain? So if I say HDFS DFS minus ls, that will show me how many part files I have, and if there is one part file, it basically confirms that there was one reduce task which was running and which has given me the output. Now we can choose this one, which is part-r 1, 2, 3, 4, 5, and let's do a cat to see how does my MapReduce output look, and let's have a look what it has done. And if you see here, depending on the URLs which were existing in the file, might be multiple entries of the same URL which were visited by users in different location, my MapReduce has looked at the URLs as the key, the count of those URLs as the values, and has given me a cumulative count of how many times a particular URL was visited. And if I see here, the highest count for URL 1 says that that was the website which was mostly visited by users across different locations. And if we look at URL 11, that is the least which is visited by the users. So this is a simple example of MapReduce where we created our own code, where we wrote our own mapper, reducer, and driver program. We packaged it as jar, and then we ran it over a cluster. Now at the same time, if I would want to look at my job which has run, I can always go to the resource manager UI. Now that could be from an Apache cluster or from a Cloudera cluster or Hortonworks cluster, and we could always click on YARN as a service in terms of Cloudera or Hortonworks. In terms of Apache, you would have to manually go to your resource manager UI. Now since my application completed successfully, I can look for it in history server. So when I click on history server, it shows me the URL count. So that is what we had specified in my driver program, that my job would be called URL count. And here I can look at this one, which shows me that there was one map task and one reduce task which ran. Well, we can always go and look into the logs to see more details if we are interested in, and we can click on full log, which can then give me a detailed information of what happened when the job ran, on how the container was allocated, how the container moved from request to being initiated to being used to being released. We can always look into the log here. Now we can also go back here and we can just look at the map task. So it tells me this is the map task which ran, and it basically, if you click on this, it tells me so it ran on a particular node which is 10.2, and we can always look at task specific logs. And similarly, we can also look for the reduce task which completed, and if you click on the task, it shows you which node was used for our job. So if we had a really huge file, we could have multiple map tasks, Or if we had similar files placed in a directory, then our directory could be input for MapReduce to give us the count. Now there are a lot of traditional examples of MapReduce. You can always search on GitHub. You can always look on your cluster for the default programs. So for example, here in Cloudera cluster, we have opt, Cloudera, parcels, cd, h, lib, Hadoop, MapReduce, and then I can search for MapReduce related jar files. For example, this is the one which exists, or I can always look into Hadoop MapReduce, just do a complete listing. And that shows me we have, say, Hadoop MapReduce client. So this is all also something which can be used. So we could just look in this one, and if you would want to see what are the programs or what are the classes already available in these jars, all you need to do is just go here and say Hadoop jar, and that shows me all the programs which are part of this jar file. Similarly, we could have looked for Hadoop MapReduce examples, and here I could look at all the programs. So there is a traditional word count program which is existing in this jar file, and if you would want to run this, then or any of these programs, you would have to specify your input or out. So this is a quick demo on your MapReduce where we have not used a default one, but we have written our own code to solve our own use case of looking into a particular file which has URLs with their count of visits, and then we would want a cumulative count by doing a MapReduce kind of processing to list down all the URLs which were most frequently accessed and URLs which were least accessed by the users.
So before we look into the demo on how YARN works, I would suggest looking into one of the blogs from Cloudera. So you can just look for YARN untangling, and this is really a good blog which basically talks about the overall functionality which I explained just now. So as we mentioned here, so you basically have the master process, you have the worker process which basically takes care of your processing, your resource manager being the master and node manager being the slave. This also talks about the resources which each node manager has. It talks about the YARN configuration file where you give all these properties. It basically shows you node manager which reports the amount of resources it has to resource manager. Now remember, if worker node shows 8 into 8 CPU cores and 128 GB RAM, and if your node manager says 64 V cores and RAM 128 GB, then that's not the total capacity of your node. It is some portion of your node which is allocated to node manager. Now once your node manager reports that, your resource manager is requesting for containers based on the application. What is a container? It is basically a logical name given to a combination of vCore and RAM. It is within this container where you would have basically the process running. So once your application starts and once node manager is guaranteed these containers, your application or your resource manager has basically already started an application master within the container. And what does that application master do? It uses the other containers where the tasks would run. So this is a very good blog which you can refer to, and this also talks about MapReduce. If you have already followed the MapReduce tutorials in past, then you would know about the different kind of tasks, that is map and reduce, and these map and reduce tasks could be running within the container in one or multiple. As I said, it could be map task, it could be reduce task, it could be a Spark based task which would be running within the container. Now here we can also give a YARN command. So let me just clear the screen and I will say YARN, and that shows me different options. So apart from your web interface, something like web UI, apart from your YARN's web UI, you could also be looking for information using YARN commands here. So these are some list of commands which we can check. Now you can just type in YARN and version if you would want to see the version, which basically gives you information of what is the Hadoop version being used and what is the vendor specific distribution version. So here we see we are working on Cloudera's distribution 5.14, which is internally using Hadoop 2.6. Now similarly, you can be doing a YARN application list. So if you give this, that could be an exhaustive list of all the applications which are running or applications which have completed. So here we don't see any applications because right now probably there are no applications which are running. It also shows you could be pulling out different status such as submitted, accepted, or running. Now you could also say I would want to see the services that have finished running. So I could say yarn application list and app states as finished. So here we could be using our command. So I could say yarn application list, and then I would want to see the app states, which gives me the applications which have finished. And we would want to list all the applications which finished. Now that might be applications which succeeded, right? And there is a huge list of application which is coming in from the history server, which is basically showing you the huge list of applications which have completed. So this is one way. And then you could also be searching for one particular application. If you would want to search a particular application, if you have the application ID, you could always be doing a grep. That's a simple way. I could say basically let's pick up this one, and if I would want to search for this, if I would want more details on this, I could obviously do that by calling in my previous command, and you could do a grep if that's what you want to do. And if you would want to search, is there an application which is in the list of my applications that shows my application? I could pull out more information about my application. So I could look at the log files for a particular application by giving the application ID. So I could say yarn logs. Now that's an option. And anytime you have a doubt, just hit enter. It will always give you options what you need to give with a particular command. So I can say yarn logs application ID. Now we copied an application ID and we could just give it here. We could give other options like app owner, or if you would want to get into the container details, or if you would want to check on a particular node. Now here I'm giving yarn logs, and then I'm pointing it to an application ID, and it says the log aggregation has not completed. Might be this was an application which was triggered based on a particular interactive shell or based on a particular query. So there is no log existing for this particular application. You can always look at the status of an application. You can kill an application. So here you can be saying yarn application, and then what would you want to do with an application? Hit and enter. It shows you the different options. So we just tried app states. You could always look at the last one which says status, and then for my status I could be giving my application ID. So that tells me what is the status of this application. It connects to the resource manager. It tells me what's the application ID, what kind of application it was, who ran it, which was the queue where the job was running, what was the start and end time, what is the progress, the status of it, if it is finished or if it has succeeded. And then it basically gives me also an information of where the application master was running. It gives me the information where you can find this job details in history server if you are interested in looking into. It also gives you a aggregate resource allocation which tells how much GB memory and how many C core seconds it used. So this is basically looking out at the application details. Now I could kill an application if the application was already running. I could always do a yarn application minus kill, and then I could be giving my application. Now I could try killing this, however it would say the application is already finished. If I had an application running and if my application was already given an application ID by resource manager, I could just kill it. I can also say yarn node list, which should give me a list of the node managers. Now this is what we were looking from the yarn web UI, and we were pulling out the information, so we can get this kind of information from your command line. Always remember and always try to be well accustomed with the command line, so you can do various things from the command line, and then obviously you have the web UIs which can help you with a graphical interface easily able to access things. Now you could be also starting the resource manager, which we would not be doing here because we are already running in a cluster. So you could give a yarn resource manager. You could get the logs of resource manager if you would want by giving yarn daemon. So we can try that. So you can say yarn and then daemon. So it says it does not find the daemon. So you can give something like this, get level, and here I will have to give the node and the IP address where you want to check the logs of resource manager. So you could be giving this, for which we will have to then get into Cloudera manager to look into the nodes and the IP address. You could be giving a command something like this, which basically gives you the level of the log which you have, and I got this resource manager address from the web UI. Now I can be giving in this command to look into the daemon log, and it basically says you would want to look at the resource manager related log, and you have the log4j which is being used for logging. The kind of level which has been set as info, which can again be changed in the way you're logging the information. Now you can try any other commands also from YARN. For example, looking at the YARN rm admin. So you can always do a YARN rm admin, and this basically gives you a lot of other informations like refreshing the queues or refreshing the nodes, or basically looking at the admin ACLs or getting groups. So you could always get group names for a particular user. Now we could search for a particular user such as YARN or HDFS itself. So I could just say here I would want get groups, and then I could be searching for, say, username HDFS. So that tells me HDFS belongs to a Hadoop group. Similarly, you could search for, say, MapRed, or you could search for YARN. So these are service related users which automatically get created, and you can pull out information related to these. You can always do a refresh nodes kind of command, and that is mainly done internally. This can be useful when you're doing commissioning, decommissioning. But then in case of Cloudera or Hortonworks kind of cluster, you would not be manually giving this command, because if you are doing a commissioning, decommissioning from an admin console, and if you are an administrator, then you could just restart the services which are affected, and that will take care of this. But if you were working in an Apache cluster, and if you were doing commissioning, decommissioning, then you would be using in two commands: refresh nodes, and basically that's for refreshing the nodes which should not be used for processing. And similarly, you could have a command refresh nodes which comes with HDFS. So these are different options which you can use with your YARN on the command line. You could also be using curl commands to get more information about your cluster by giving curl -x and then basically pointing out to your resource manager web UI address. Now here I would like to print out the cluster related metrics, and I could just simply do this, which basically gives me a high level information of how many applications were submitted, how many are pending, what is the reserved resources, what is the available amount of memory or CPU cores, and all the information. Similarly, you can be using the same curl commands to get more information like scheduler information. So you would just replace the metrics with scheduler, and you could get the information of the different queues. Now that's a huge list. We can cancel this, and that would give me the list of all the queues which are allocated and what are the resources allocated for each queue. You could also get cluster information on application IDs and status running of applications running in YARN. So you would have to replace the last bit of it, and you would say I would want to look at the applications, and that gives me a huge list of applications. Then you can do a grep, and you can be filtering out specific application related information. Similarly, you can be looking at the nodes. So you can always be looking at node specific information, which gives you how many nodes you have. But this could be mainly used when you have an application which wants to, or a web application which wants to use a curl command and would want to get information about your cluster from an HTTP interface. Now, when it comes to application, we can basically try running a simple or a sample MapReduce job, which could then be triggered on YARN, and it would use the resources. Now I can look at my application here, and I can be looking into my specific directory, which is this one, which should have a lot of files and directories which we have here. Now I could pick up one of these and I could be using a simple example to do some processing. Let's take up this file. So there is a file and I could run a simple word count, or I could be running a Hive query which triggers a MapReduce job. I could even run a Spark application which would then show that the application is running on the cluster. So for example, if I would say Spark to shell. Now I know that this is an interactive way of working with Spark, but this internally triggers a Spark submit and this runs an application. So here when you do a Spark to shell, by default it will contact YARN, so it gets an application ID. It is running on YARN with the master being YARN, and now I have access to the interactive way of working with Spark. Now if I go and look into applications, I should be able to see my application which has been started here, and it shows up here. So this is my application 3827 which has been started on YARN, and as of now we can also look into the YARN UI, and that shows me the application which has been started, which basically has one running container which has one CPU core allocated, 2 GB RAM, and it's in progress, although we are not doing anything there. So we can always look at our application from the YARN UI, or as I mentioned, from your applications tab within YARN services, which gives us the information, and you can even click on this application to follow and see more information, but you should be given access to that. Now this is just a simple application which I triggered using Spark shell. Similarly, I can basically be running a MapReduce. Now to run a MapReduce, I can say Hadoop jar, and that basically needs a class. So we can look for the default path, which is opt cloudera parcels cdh lib hadoop MapReduce Hadoop MapReduce examples, and then we can look at this particular jar file, and if I hit on enter, it shows me the different classes which are part of this jar. And here I would like to use word count, so I could just give this, I could say word count. Now remember, I could run the job in a particular queue by giving in an argument here. So I could say -d mapred dot job dot queue dot name, and then I can point my job to a particular queue. I can even give different arguments in saying I would want my MapReduce output to be compressed, or I want it to be stored in a particular directory, and so on. So here I have the word count, and then basically what I can be doing is I can be pointing it to a particular input path, and then I can have my output which can be getting stored here, again a directory which we need to choose, and I will say output new, and I can submit my job. Now once I've submitted my job, it connects to resource manager. It basically gets a job ID, it gets an application ID, it shows you from where you can track your application. You can always go to the YARN UI and you can be looking at your application and the resources it is using. So my application was not a big one, and it has already completed. It triggered one map task, it launched one reduce task. It was working on around 12,466 records, where you have then the output of map, which is these many number of output records, which was then taken by a combiner, and finally by a reducer, which basically gives you the output. So this is my YARN application which has completed. Now I could be looking into the YARN UI, and if my job has completed, you might not see your application here. So as of now, it shows up here, the word count which I ran. It also shows me my previous Spark shell job. It shows me my application is completed, and if you would want further information on this, you can click and go to the history server if you have been given access to it, or directly go to the history server web UI where your application shows up. It shows how many map and reduce tasks it was running. You can click on this particular application, which basically gives you information of your map and reduce tasks. You can look at different counters for your application, right? You can always look at map specific tasks. You can always look into one particular task, what it did, on which node it was running, or you can be looking at the complete application log. So you can always click on the logs, and here you have click here for full log, which gives you the information, and you can always look for your application, which can give you information of app master being launched, or you could have search for the word container. So you could see a job which needs one or multiple containers, and then you could say container is being requested, then you could see container is being allocated, then you can see what is the container size, and then basically your task moves from initializing to running in the container. And finally you can even search for release, which will tell you that the container was released. So you can always look into the log for more information. So this is how you can interact with YARN. This is how you can interact with your command line to look for more information, or using your YARN web UI, or you can also be looking into your Hue for more information. Thank you and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.